we have a couple of choices, design choices, and adjustable parameters that I've not mentioned too explicitly before. Amongst these are the activation function, and most famous are, on one hand, McCulloch-Pitts, which is really the hard threshold, and then people use a hyperbolic tangent or for instance, the logistic. Will give you a nice smooth sigmoid depending on the choice of alpha. McCulloch was, I think, a biologist, and Pitts was a theoretician. And if you're interested in the early days of neural networks, there's a nice collection called Talking Neural Nets with interviews of these people, many of whom are still alive today. And there are, for instance, a couple of anecdotes surrounding both McCulloch and Pitts, and this was during World War II. So everybody was drafted either into the effort to build the atomic bomb, if those were scientists, or direct to the army. And so in quite a few of these stories, you hear what they experienced in the war, and they had fun in their way. So for instance, there was one guy, Latvian, giving the interview, who kept sending Pitts, who was working at Kellex, and Kellex was one of these companies involved in the atomic bomb, who kept writing him postcards written in German. Enclosed, you'll find the secret, the secret documents. And these postcards never got there. and they were wondering what happened to them, if people had been dissecting the periods on these postcards or whatever. And then there were, of course, serious security measures. And then there was always a red waste basket and a green waste basket. The red waste basket was for the sensitive material. And here Pitts was feet on his desk, cracking peanuts and throwing the shells into the red waste basket, the contents of which had to be burned in the presence of two witnesses in the basement. And in came the general screaming, "What are you doing? You know, wasting people's resources by throwing peanut shells in the red basket." And then Pitt said, "Well, look at the shells." And on each shell, so on each of the nutshells, he had inscribed alpha or beta, the magic Greek letters used in formulas. So the peanuts had to be taken down and burned in the presence of two witnesses. So this was how they damaged the war effort. And then there's another story I like, namely the atomic energy effort was being embarrassed by the fact that the draft laws gave no exclusion of scientific personnel. So they took even the scientists and turned them into cannon fodder. The result was that good technical people were being drained from Kellex. They didn't know how to stop it. And then a solution occurred, and he writes, he wasn't sure whether the solution occurred by design or accident. There was a particular psychiatrist whom I accused of arranging it. He refused to deny it, but he also refused to affirm it at the time. Installed as senior psychiatrist in the 42nd Street was A.A. Brill, the fellow who had translated Freud to English. Now, Brill was a nut. He was crazy. He had the theory that schizophrenia had to do with symbolism, and since mathematicians dealt with symbols, etc. So once Brill was put in office, so the psychiatrist was put in office, and mind you, nobody had instructed him. It was his own Meshuggahs that kept things going. Scientists and engineers were being turned down from the army, right and left, for being pre-schizophrenic, pre-psychotic, and so on. It was highly demoralizing to the physicists and mathematicians concerned who took seriously the Schmuck's diagnosis. So in went this Walter Pitts, who at that time wore a beard, and he walks in, and the psychiatrist looks at him and says, "Young man, why do you wear a beard?" And Walter says, old man, why do you? And from that point, it was straight downhill, and he came out, so Walter Pitts came out with the diagnosis of frank schizophrenia, which probably saved his life, or perhaps saved his life, but also, he writes, upset him considerably because he was a fragile person. And then he wanted to volunteer, and Letwin had to talk him out of joining the army. And so you know, a whole book full of anecdotes, and some of them are quite good. So, you know, this is the Pitts in that activation function. Just to justify, you know, why we're talking about this here. So, adjustable parameters. Then there is the cost function for parametrization, or for optimization. Well, people can either try and predict class labels, or you can try and predict continuous outputs, as in regression. In that case, least squares can be used, or especially for classification, entropy fit may be used. Then there is the question of the network size and architecture. And that is the toughest one, really, because you have so many degrees of freedom here. So how many hidden layers, and how many neurons per layer, and so on. And to prevent overfitting, there are a couple of regularization strategies that people use. So regularization can either be used by using a bias during training, which favors small weights, or you can prune networks. So first grow the full network, and then eliminate those neurons whose elimination does the least damage possible. So keeping these weights down is called shrinkage. And sometimes people use tied weights. So especially in image processing, you can build invariances into these networks by requesting that some weights be the same as others. And I can show you the effect of using different architectures for an example that by now you know very well. So in this corner you see a training set, and the ideal decision boundary, and plotted here are the decision boundaries that you obtain for different numbers of perceptrons in the hidden layer. So a single perceptron in the hidden layer will give you just a linear classifier, and there are 2 perceptrons. And you see that because this is not a perfectly sharp edge, you can tell that I used an activation function, which was also somewhat smooth. Then 3 perceptrons, which, so arguably here 2 or 3 would be optimum, and then you have 4, 5, 6. And what you start seeing here as you include too many perceptrons is overfitting. So you get a lot of variance. Your result looks very different depending on which set you trained on. Then there's also the question of the optimization strategy. And since this is just an abstract global optimization problem, people have used everything that you normally use in global optimization. You've seen, or we have discussed just steepest descent, which would be the baseline. But you can also endow the system with an artificial momentum term. So if you look at some energy function, and you do steepest descent, let's say from this point here, you would normally just fall into the closest minimum and be stuck there. And the idea is that with a momentum term, that you can, you have like a ball rolling around the surface, and the ball has a non-zero mass. So the idea is that your system can escape local minima by shooting over smaller barriers. And you need to couple, if you introduce a momentum term, you also need to couple this with some kind of dissipative term. You can invent all kinds of things here. People have used natural gradients here, and then schemes that approximate the curvature over time, so from a series of gradient estimates like Broyden, Fletcher, Goldfarb, Shano, and others. So everything that you've seen in gradient-based optimization you can use here. And then people have also used evolutionary strategies, genetic algorithms, and simulated annealing, and so on. Now, I've mentioned the gradient a lot, and the reason is, and this is also the reason why they had this, why neural networks had this comeback in the 80s, is back-propagation. It took a surprisingly long time for people to come up with this, but in hindsight, these things are always easy. But if you look at the output of your neural network, you have a summation over weights. And this is, let's say, in layer number R. And these weights are multiplied with the outputs of previous layers. And the outputs of previous layers are given by the activation function, so typically the sigmoid. And in this activation function, you now have in turn the input from, let's say, the weights at some previous layer R minus 1, which are again multiplied with the activation function of, and now you can nest this as often as you have layers in your neural network, and all of this will give you the estimated output. And now really what you do is when you now evaluate, for instance, this least squares cost function here, the square deviation of your prediction from the ground truth, you can take the squared error and you can differentiate it with respect to all these weights. And because you have these nested functions, you need to use the chain rule iteratively. So again and again. As often as you have layers in your neural network. And well, this will give you your gradients, provided that these sigmoids are differentiable functions. Okay, and this is all. But as I said, it has taken people a while to find this out. So I now want to talk about a couple of special neural networks. First, so-called self-association networks, which you can use to find your principal components. So if you remember in the PCA lecture, what we did, we had found some approximation, which I'm calling So W is your first principal component, and X would be your, so this would be your first principal component. This would be your observation. And if I project my observation onto the first principal component, I get out the score, so the coordinate in this new rotated coordinate system. And if I now multiply the score with the principal component, I obtain an approximation to my original observations. So this would be the reconstruction overall. Okay, and the idea now is that you build a neural network with a couple of inputs. So let's say for a 4D space, we would have 4 inputs. And let's assume that I have centered the data, so I don't need the bias term. My activation function in this case is just the linear function. And I now want to map it back to a higher dimensional space. So these would be the weights W1 and so on up to WP. And these are, because I multiply here, these are the same weights, W1 up to WP. So at this stage here, I would have the scores. And if I now multiply the scores with the principal component itself, I obtain my reconstruction. So overall, you see we have created some kind of bottleneck. So I have 4-dimensional data. I squeeze it into a bottleneck. I inflate the dimensionality again to using the same parameters to obtain 4-dimensional data. And well, if I use PCA in the sense of getting the best linear approximation, then I want this output to be as similar as possible to that input. So my input was X, and my output was X hat. And then I can request, for instance, that the squared error be minimal. So the squared error and now this is summed over all observations that I have in my data. So you connect or you compare the output to the input, and you want them to be as similar as possible. And well, somebody has called this a self-association network. Okay, now we again want to find the optimum parameters. So we differentiate with respect to these weight vectors. Well, I could formulate this, or I could add an extra parameter here if you want to make an online algorithm. So I could say that this is gamma to the power of n minus I. So the more recent will be forgotten more. That's the more distant ones should be forgotten more. This is why I put minus I, that's right. And this gamma, I also need to introduce it somewhere there. So if I include a parameter like that, it will induce some kind of exponential forgetting. Which will be useful for online learning. Okay, let me write this out once more. So we have and there are some W's missing here. There is W transpose W missing, sorry. Okay. One more. Okay, now I have all the W's I can possibly want. And now I could either at this stage already, I can make two different approximations, and that will result in two different update algorithms. So an approximation made by Amari in 1978 would be to say that at this stage, W transpose W should be around 1. And then I'm left with an error which is only that. And in the way we had derived PCA, we had strictly demanded that the norm of the vectors W be 1. But here it is not explicitly enforced, so it will be hopefully close to 1, but need not be exactly 1. Okay, this is why it's an approximation. And now we can finally differentiate with respect to the weight vectors. First term is independent of the weights, and the second term will give me that. And I can then formulate an update saying my new weight should be the old one, minus magic step size times that. And the magic step size here relates to the choice of gamma. Now, alternatively, we can not make this approximation here and first compute the derivative and then make it. And that will give us an update formula which is due to Oya. few years later. So in that case, the derivative will be -4 times that plus and no, I'm rewriting this term so I can more conveniently differentiate with respect to w. Note that this is a scalar, so I can also write this is w transpose xi times xi transpose w times w transpose w. And differentiating the first part will give me and differentiating the second part, this is hold on, I will rewrite this as w transpose xi squared times w transpose w. So this gives me, don't copy down too early. So this will be twice w transpose xi times the inner product, or the inner derivative, this is xi, plus does that look right? -4 there's w transpose w missing here. I think that looks reasonable. Okay, and so OER only at this stage makes the approximation of saying that that should be roughly the same as 1, such that this term will then partially cancel out with that one. And we then find W new is W old magic step size. I can omit those constant factors or absorb them in the step size. Okay. So those are two different rules where the approximation regarding this norm of W are made in different instances, and both give you online algorithms to find the first principal component. And you can simultaneously find more than one principal component by looking at the residual that's left after you've projected out the contribution of the first principal component, and then fitting a second inner perceptron for the second principal component. So you can also do that online. But overall, convergence really becomes better if you enforce this normalization by saying so if that is W nu, by getting a norm of 1. And many of the algorithms from signal processing and so on, many of these adaptive algorithms, they have been formulated in terms of neural networks. You have to decide for yourself if you find that a natural interpretation or not. Okay, then there are other types of neural networks that I want to mention. The perceptron networks that we have seen have units that are infinite. So remember those perceptrons, those are really straight lines and they extend throughout feature space. And on the one hand, that allows you to model complex decision surfaces using few hidden neurons. But on the other hand, it makes the whole system hard to train. And instead, people have thought about using more local basis functions. In particular, radial basis function networks. Use more local basis functions. And the idea is to distribute these basis functions. They can be Gaussians or multiquadrates or thin plate spline functions, but the most typical is to use Gaussians to distribute them in space, and then formulate the approximation problem as follows, to say that your prediction at a location X in feature space will be some offset plus a linear weighted combination of these basis functions, which I am calling G because they are often Gaussians. And then having some norm of the location X where I want to make a prediction minus the location where that basis function is centered. So if you think not of a single prediction but of multiple predictions, I can rewrite this in terms of vectors and say, in the training phase, I want to make a prediction at a total of n sites. And I do so by multiplying a vector of weights with a matrix of transformed coordinates. So overall, I have a matrix here with m by n entries. And I can collect this in a matrix which I may call X. So you see that my original observations have been, or perhaps X tilde, you see that my original observations X have been somehow non-linearly transformed and have obtained a new dimensionality. My original matrix X, my original observations were a matrix of dimensions P by N, and I now have a matrix of dimensions M by N. And M may be larger or smaller than P. Now, if I fix the positions of these weight functions, so if I have settled on a particular form for these weight functions, and if I have settled on their locations, finding the remaining parameters is easy. It boils down to just least squares problem. However, finding the right norm, so for instance, I may have a covariance function. So let's say finding the proper parametrization of G. And the locations mu. That is typically hard. So something that's often done is that the locations are first fixed by clustering the data, and then given those locations, the parameters beta are found by fitting this least squares problem. And this was the state of the art until, let's say, the mid-90s. In the late 90s, this paper came out, which was written by the then champions of the RBF method, people around Girosi, and the champions of the support vector machine. And on a digit recognition data set, you need to look at the test errors. The RBF, Radial Basis Function network, got a test error of 6%, and the support vector machines got a test error of only 2%. And so, in a way, this era came to an end. RBFs, if you use a cheap heuristic to find the locations for the basis functions, are much cheaper to fit than a support vector machine, but these locations may be suboptimal. And the support vector machine jointly finds both the locations for the basis functions, the support vectors, and the optimum coefficients. And this is the reason why support vector machines are nowadays a very, very popular method. This is also why we're going to study it in much detail next week. As a, we have some tape left? 20 minutes will be enough. So my final, no, won't be enough. Let's have a break.